All right, I'm going to go ahead and do these problems. Some of them we did in class, and I'm just going to redo them for anybody that was absent on Friday. This is probably my third time doing the videos. If I stumble over my words, forgive me. It's been a long day. And like I said, this is the third time I've made this video because the software keeps kicking me out. So this is my last and final attempt. Hopefully this works. This will be kind of long. Please feel free to just advance it ahead and try these problems out. And don't feel like you've got to watch this whole thing. It'll probably end up being a total of about 16 minutes based on my previous attempts. Okay, so here we go. So a sample of gas occupies 150 milliliters at 25 degrees Celsius. What is its volume when temperature is increased to 50 degrees Celsius? The pressure is constant. Well, yay, pressure is constant, so I can not deal with pressure. Now, the first thing I noticed right away is I've got two temperatures and they're both in Celsius, so I need to convert them. 25 plus 273.15 is equal to 298.15 degrees Kelvin, and the other temperature is 50 degrees Celsius. There we go. All right, I've got my temperatures converted. They're in Kelvin, which is perfect for gas problems, and I'm ready to fill in my chart. So the gas at the start occupies 150 milliliters, and it had a temperature of 298.15 degrees Kelvin. My volume is my unknown, and my temperature I've converted to 323.15 degrees Kelvin. Now, I'm looking at this and the effect. So my temperature has gone up. If my temperature goes up, I expect my volume will go up too. So the formula I'm going to use for every single one of these problems is P1 times V1 over T1, which is my initial conditions, will equal P2 V2 over T2, which is my final conditions. Remember, this formula is on your reference table, and I'm just going to use this and cross off what I don't need, what is remaining constant. So in this problem, my pressure is remaining constant, so I can go ahead and cross that off. Now I'm going to substitute in the values that are in the table. So my first volume is 150 milliliters. My first temperature is 298.15 degrees Kelvin, and that's going to be equal to the volume, which I'm trying to figure out, and the final temperature. To solve all of these problems, I am always going to cross multiply. Whenever I have an unknown on one side of an equation, I need to cross multiply to find the answer, as long as I've got two fractions. So I'm going to multiply 150 milliliters by 323.15 degrees Kelvin will equal, now I'm ready for these guys, my volume and the final temperature, or the initial temperature, 298.15 degrees Kelvin. There we go. Now, if you remember your algebra, in order to get rid of and get my variable isolated, I need to divide this number, because they're multiplying this times my variable. To get rid of it, I'm going to need to divide by it. Now, whatever I do to one side of the equation, I need to do to the other side of the equation. So there's my 298.15. This is now gone. I've gotten rid of that. So when I solve that fraction, I'm going to get my final answer, which is going to give me a volume of, I'm going to pause this and then put it in my calculator. Okay, so that gives me a volume of, in my calculator, 162.58. I'm rounding there. All right, now here comes the part for where I have to figure out my significant figures. I look at this number, decimals absent, so I'm going to start from the Atlantic side, and I've got 2 in this one. I've got 2 in this one. I have 1 significant figure in this answer here. Now, this is where in class, I didn't see that 50 degrees. So when I looked at it, everything had 2 significant figures. The 50, however, is 1 significant figure. So my answer has to be a volume of 200. And that's going to be milliliters. So my final answer is 200 milliliters. And I'm going to put a box around it. You can see that these problems get very messy looking. It's super important for you to put a box around your final answer. All right, on to the next one. The pressure in a bicycle tire is 105 psi at 25 degrees Celsius in Phoenix. You take the bicycle up to Flagstaff where the temperature is -5 degrees Celsius. What is the pressure in the tire? It tells us that the volume is constant. I don't need to think about the volume. All right, I do see I've got 2 temperatures here. I've got a starting, initial temperature, and a final temperature, and they're both in Celsius. So 25 plus 273.15 is equal to 298.15, which is the same temperature I just calculated in the problem above. Now the next one is a -5 plus 273.15 is equal to 268.15 Kelvin. All right, so now I'm ready to get rolling with my problem. So the pressure in the bicycle tire is 105 psi. So my starting pressure is 105 psi. And I've got my new temperature, which I converted to Kelvin, is 298.15. Now, the final temperature is 268.15, and I need to find the pressure. Looking at my variables, it looks like my temperature is going down. If temperature is going down, my pressure should definitely go down as well. I'm going to use the formula P1 V1 over T1, initial conditions, and P2 V2 over T2, my final conditions. So now I'm going to substitute in my numbers. So for my pressure, I had 105 psi. My volume I don't need, so I can cross those off. That's staying the same. That's going to be over my temperature initially, which was 298.15 degrees Kelvin. And my pressure I'm going to be solving for, and my final temperature is 268.15 Kelvin. All right, as always, I'm going to cross multiply to solve this problem. So when I cross multiply, I get 105 psi times 268.15 degrees Kelvin. Now I'm ready for this one. Pressure 2 times 298.15 degrees Kelvin. Now I need to get rid of this guy so I can have my variable by itself. If I do it on that side, I need to do it on this side. That's gone. And now I'm ready to calculate my answer. All right, my answer is a pressure equal to 94.43. Now, I need to go back through and check about my significant figures. I've got 3 in this one. I've got 2 in this one. I have 1 in this number there, 1 significant figure. So I need to be sure that my answer has 1 significant figure. So my final answer is going to be 90. And that units are going to be psi. And I put a box around it so that I can find my answer in all this mess. On to number 3, charging along like a herd of turtles. What will be the new pressure if 250 centimeters cubed of a gas at standard pressure, standard pressure, is compressed to a volume of 150 centimeters cubed? Temperature is constant. We don't need to factor in temperature. So let's see here. I don't have to convert anything because temperature is not a factor here. Still going to use the same formula. P1, V1, T1 is equal to P2, V2, T2. I don't need temperature because that's staying constant in my problem. I can cross it off and substitute in my values. So my pressure, I need to fill them in my chart here. I'm getting ahead of myself. The volume at the start is 250 centimeters cubed. It's at standard pressure. Now it's not telling me a unit, so I can choose whatever of the standard pressure units I want. I'm going to choose 1 atmosphere because 1 is an easy number to do mathematically. So I'm going to say my starting pressure is 1 atmosphere, which is standard pressure. It's compressed to a volume of 150 centimeters cubed, and I need to find the pressure. Now, looking at my effect, well, my volume is going down. If volume is going down, my pressure should go up. Okay, let's substitute them in. So, my pressure at the start is 1 atm. My volume is 250 centimeters cubed equals my pressure 2 times my volume 2. This is a nice one because this is one of those ones where I don't really have to cross multiply. I just can jump right in it. I need to isolate my variable, so I'm going to divide this by 150. And if I do it on that side, I got to do it on this side. So that takes that away, and now I'm left with just me and my calculator. Okay, so my answer is a pressure of 1.666, and it just keeps on a-rolling. So let's check my sig figs. I've got 2 here. I've got 2 here. So I must need to have 2 significant figures in my answer. My final answer is a pressure of 1.7, and my unit is going to be atmosphere. And I put a box around it. Beautiful. Here we go with number 4. What would be the new volume if 250 centimeters cubed of a gas at 25 degrees Celsius and 730 millimeters of mercury pressure were changed to standard conditions of temperature and pressure? So we do have temperature and pressure in this one also. So I see I've got a Celsius number, so the first thing I'm going to do is convert it. Okay, so what would be the new volume? So volume is what I'm going to be solving for. My starting volume is 250 cm cubed, and my temperature is 298.15 degrees Kelvin. My pressure is 730 millimeters of mercury. So notice how the mercury is left off just because it makes it too long. So I'm looking for my final volume. I've got conditions of standard temperature and pressure. Well, this is where you're going to grab your reference table and you're going to look toward the bottom. And the first thing you'll see is standard temperature. You have 2 choices, one in Kelvin and one in Celsius. Being a gas law problem, I want to grab the one that is in Kelvin. Standard temperature is 273.15 Kelvin. Now, the pressure. I've got 4 different choices. I've got it in atmospheres, I've got it in PSI, I've got it in kilopascals, and I've got it in millimeters of mercury or torr. Well, millimeters is the best one to use because it's going to match what I already have in my problem. This unit here is the best unit to match to. So 760 millimeters of mercury is standard pressure. Now, my effect. My pressure is going up. My temperature is going down. So let's take a look and see what happens. We're not going to do number 5. Number 5 is just it's on 2 different pages. So I'm going to actually do my work for this problem down below since I have a lot more room. So I have my B1, V1. Are you sensing a pattern here? It's the same thing every single problem. I always start with that formula, and then I just substitute in what I have. My pressure at the start is 730. My volume at the start is 250. My temperature at the start is 298.15. Now, my pressure at the end is 760. And my temperature, well, my volume is what I'm finding. My temperature at the end, my final temperature, is 273.15 Kelvin. As always, I'm going to cross multiply. Let's do these one at a time. The first one I'm going to do is right here. So I've got 730 times 250 times 273.15 is equal to, now I'm ready for these two, 298.15 times 760 times my volume. Okay, now this is the first time we've had multiple variables other than the question above. And let's see how we do this one. So, in order to isolate my variable, I have to do the same thing I've been doing all along. These two numbers are multiplied together. So I could either multiply them together and then transfer that number over, or I could just divide by these and if I do that on that side, I can do that on this side. Now I've gotten rid of that. Same thing I've been doing all along. I've isolated my variable. The reason why I like to do this and not multiply them together in different steps and write that down is because the chance that I'm going to write a number wrong exists. If I do it this way, I've usually got less to transfer into my calculator, and I can actually do this in one big long step. So the first thing I'm going to do is I'm going to multiply all the numbers together on the top. Then I'm going to get an answer, and then I'm going to divide it by these two numbers on the bottom on the denominator multiplied together, and I can do that using parentheses. I'm going to pause the video and I'll get you your answer. All right, so your answer is a volume of 219.996.4 and so on. Let's go ahead and take a look at our significant figures. So there are 2 here, there are 2 here, there are 2 here. So it looks like I need to have 2 in my answer. So my final answer is going to be a volume of 220. And my unit has to be, it's volume. So my volume is centimeters cubed. Put a box around it. There's my volume. All right, we've got 3 more to go. If you're hanging with me, I give you a lot of credit. Let's go ahead and do these, and you'll see what answer is. I hope that some of you, these are you're trying by yourself, and you're just kind of fast forwarding through the video to see what the answers are. But if you need the step-by-step, it's right here for you. So let's get going and quit talking. At what temperature would 350 milliliter sample of gas at 30 degrees Celsius, I've got to convert it. 30 plus 273.15 equals 303.15. There's my temperature converted. And I've got 730 millimeters of pressure fit into a 250 milliliter flask at standard pressure. Okay, so let me fill in my chart. We've got 350 milliliters. There's my volume. My temperature is 303.15. My pressure is 730 millimeters of mercury. It's going to be what temperature, so I've got to solve for temperature. My final volume is 250 milliliters. And my pressure, it's standard pressure, so I'm going to look at my chart and I'm going to find the standard pressure value that has the same units as my question. So I'm looking for something with millimeters of mercury, and that would be 760 millimeters of mercury. In this question, my pressure has gone up. My volume has gone down. So let's see what happens to the temperature. Substitute in my values. And now for the final values. Now for the good old cross multiply. I'm going to do that one times this one. All right, now I'm not going to go ahead and solve this for you. You should be able to do this one by yourself. Go ahead and figure out what the answer is here, and I'll show you. So you do the math for this one. Okay, when I'm finished with the math, I get a temperature of 225.43. I'm going to check my significant figures here. I've got 2 here, I've got 1 here, I've got 2 here, I've got 2 here. My final answer should be with 1 significant figure. So my final answer should be and I'm done with that problem. All right, 2 more to go. Now this next one is pretty straightforward. It's very similar. So let's just jump right into it. We've got a 475 centimeters cubed sample at standard temperature and standard pressure is allowed to expand until it occupies a volume of 600 centimeters cubed. At what temperature would the gas return to standard pressure? So let's go ahead and fill these in. So we've got our volume, we've got our temperature, and standard pressure. It's not giving me any specific standard pressure that I have to use, so I'm going to use whatever I like. So 1 atmosphere. It's at standard pressure at the start. Now I'm going to go ahead and my final volume has to be 600. Notice how we've got a decimal point here. I'm going to keep that decimal point with everything. And that's going to be centimeters cubed. And then my pressure is standard pressure, 1 atmosphere. Well, my pressure is not changing at all, so I can actually cross this out. What's changing here is my volume is going up. So let's see the effect of volume going up on temperature. So, got my usual formula. I don't have any pressure, so I don't need to put that one in. So I'm really looking at my volume of 475 over my initial temperature. And here I've got my final volume over my temperature, which I need to determine. Okay, I'm going to pause the video so you can do the math, and then I'll show you what the answer is. All right, after doing the math, I've got a temperature equal to 345.03. Now, let's look at our significant figures here. I've got 3 in this number. I've got no other numbers here except for this one. Notice the decimal is present. If the decimal is present, I'm going to start on the Pacific side. I hit my first non-zero number, and this one actually has 3 significant figures to it. So my answer has to have 3 significant figures. My final answer is going to be 345 degrees Kelvin. Be very careful if you see a decimal point, because that's going to change your number of significant figures. Now for our last box. The diagram below on the left shows a box containing gas molecules at 25 degrees Celsius and 1 atmosphere of pressure. The piston is free to move, which means it can go down or it could come back up. So first thing we're going to do is I notice that I've got a temperature here, and I'm going to read below, and maybe my temperature stays the same, but let's take a look. In the box at the right, sketch the arrangement of molecules and the position of the piston at standard temperature and pressure. Does the volume decrease significantly? Why or why not? So let's see what we've got here. It does look like I'm probably going to need to change my temperature because it's going from 25 degrees Celsius to standard temperature, so that's going to be a change. So 25 plus 273.15 equals 298.15. So that's going to be my temperature. I'm going to create a little chart over here so I can do the usual initial temperature and so on. I think my chart's going to be kind of too small, but we'll see what we can do with it. Whew, that's awful little. Here's my pressure, temperature, volume. Here's my initial conditions. Here's my final condition. So at the start, I've got a temperature of 298.15. A pressure I've got is 1 atmosphere pressure. Okay, now looking for my final conditions, it's the ending at a temperature of standard temperature, so that's 273.15. And pressure, well, if it's standard pressure at the start and standard pressure at the end, 1 atmosphere, it looks like I'm not going to have to deal with pressure at all. The pressure is not changing. But the problem is it wants to know volume, and I don't have a volume. Well, here's the tricky thing. It's proportional, right? So if I start of a made-up volume of 100 milliliters, if I say that's my starting volume, I'm going to still see the same proportion when I end. So let's go ahead and substitute these numbers in. Let me go ahead and make myself a little bit more room here. I won't do that. Guess I can't do that. I want to be able to get rid of something. Let's do a big old box. That'll give me some room to write. That's better. Okay, now that I've got myself some room to write, I'm going to go ahead and you'll never guess what the formula is. E1 V1 T1 equals P2 V2 T2. Okay, so I've already said I don't need pressure, but I do need temperature and volume. I'm going to say my starting volume is 100 milliliters. My starting temperature is 298.15 degrees Kelvin. Now, my ending volume is what I need to find. And I know my ending temperature is 273.15 degrees Kelvin. So I'm going to go ahead and cross multiply and solve for volume. All right, my ending volume is going to be equal to 91.614, blah, 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 blah. All right, now, significant figure-wise, well, here we have two significant figures in that number. We have one significant figure in this number. So I'm going to make this one significant figure. So my ending volume is 90 milliliters. I went from 100 milliliters to 90 milliliters, which means it only changed by about 10%. That's not a very significant change. So my final answer would be no. Does the volume decrease significantly? No. It only changes by 10 milliliters, which is about 10% of 100. Okay, so I've answered that question. Now I need to draw my picture. So I'm going to keep this thing straight. Just kind of roughly divide it into 10 sections. I'm going to say my lid is going to drop down to this point here. So there's my new, it's about 1/10 of the volume. Now over in the chamber here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles. So I need to draw 10 particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There I've got the same number of molecules because they're not being lost or destroyed. I've got my volume about 10% smaller than it was at the start. And I have finished this problem. Smiley face, yay. Yeah, there we go. Now, if you've watched this video all the way to the end, you can earn some bonus points. If you quietly come up and put a piece of paper on my desk that has this written on it, Maxine. If you put a piece of paper on my desk that says Maxine, I will give you some bonus points for having watched this whole video. Now, if I have a whole bunch of people that come on and drop on a note on my desk that says Maxine, oh, also put your name on it. Your name, then I will give you bonus points. But if I have everybody doing this because the word has gotten out and I'm looking at my YouTube video and find that I do not have that many people that watch the video, then all bets are off and I'm not giving bonus points to anybody. So keep it on the down low. If you watch this video, yes, you with your name, you deserve the bonus points. Okay, I'm all done and I think it's time for bed.